Today, it's my pleasure to introduce our speaker for the month, Tara Shreve. She is an Interferometric Synthetic Aperture Radar Specialist, it's a mouthful, who joined the Utah Geological Survey in 2024. She has a BS in mathematics from American University and graduated with a PhD in geophysics from the Institut de Physique du Globe de Paris in 2020, with a focus on InSAR-geodesy. She's applied InSAR to identify, interpret, and model ground deformation at remote volcanoes in Alaska, Vanuatu, Democratic Republic of Congo, and the Galapagos. Her work with the UGS to monitor different geologic processes that drive ground displacement throughout Utah, such as land subsidence, landslides, and earthquakes. So with that, I'll hand it over to Tara.
All right, thanks so much for the introduction. Let's see can everyone hear me all right? All right, sweet. So my name is Tara. I work here at the Utah Geological Survey with the Geohazards program, and I've had the pleasure of being here since last August. And when I arrived, I had many colleagues who had ideas on how we could use Interferometric Synthetic Aperture Radar, or InSAR, to look at ground displacement throughout the state. So I've had the pleasure of working in particular with these colleagues I've listed in both the hazards program, but also the groundwater program. So for this talk, I'm going to start with motivation as to the applied science questions we want to answer here at the UGS, talk a bit about the InSAR, give you a background in InSAR for those of you who may not be familiar with this technique, and then go into two different case studies in Utah, one focused on land subsidence throughout the state, and the second focusing on slow-moving active landslides. We'll then finish with some conclusions and perspectives for future work. I do want to say if anyone has any questions throughout the presentation, feel free to raise your hand and I can answer them as we go through, particularly regarding the methodology. So in regards to the applied science questions that we want to focus on here at the UGS, the first is related to aquifers within the state, and we want to better understand how aquifer storage loss is occurring in Utah due to groundwater pumping in excess of recharge. And the second question is related to landslide activity. So how is intermittent and catastrophic landslide movement in Utah triggered, and how do changes in slow-moving landslides over time maybe indicate this triggering? I'll start off by introducing synthetic aperture radar, or SAR, which is a methodology that produces fine resolution images from a radar system. This radar sensor can be mounted either on a plane or a satellite or even on a vehicle on the ground. But throughout this presentation, we're going to be focused on satellite-based radar systems. Here we can see an example of a satellite-based SAR sensor, which emits a radar signal, which is backscattered off the Earth's surface. This signal has both an amplitude and a phase. And when we take two measurements from different days, we can find the difference in that phase to be able to measure the amount the ground has moved towards or away from the satellite. So in this animation, we can see that there was, for example, a volcanic eruption, which caused subsidence at the surface, and therefore the land moved away from the satellite. If we look at a particular location on the Earth's surface and we look at the phase that was retrieved by the sensor on 2 different days spanning this event, that difference in the phase, or that red portion of the line, indicates how much the ground has moved away from the satellite. So this technique is called InSAR, and we're able to measure up to millimeter or centimeter amounts of displacement towards or away from the satellite. We can use this technique day or night, and regardless of weather, due to radar being an active remote sensing method, which allows us to be able to respond to events that may have occurred as rapidly as we can, depending on when images are acquired, without having to worry about issues like cloud coverage that may occur with optical imagery or other passive remote sensing methods. So due to the utility of this technique in earth and environmental sciences, the number of SAR satellites that are currently in orbit have increased dramatically over the past 30 years. In this figure, we can see the number of satellites that were launched in 1995, so about 4, compared to the more than 10 satellites that are currently in orbit. And there are still a few more that are planned to be launched in the upcoming years, with the most recent launch planned for the InSAR mission, which hopefully will be launched this month, but that is to be determined. Also in this figure, we can see we're categorizing these different satellites based on their wavelength. So the radar wavelength is going to be one of the ways that we decide which satellite mission we want to utilize. The satellites in the bottom portion of this figure have longer wavelengths, and longer wavelengths can penetrate through vegetation, which allow them to be more useful in certain areas of Utah, such as the Wasatch or the mountains in the Wasatch or the Wasatch Plateau, where we have quite a few landslides. However, these longer wavelengths are also less sensitive to displacement, and so we have to have larger displacements before we're able to have the signal be distinguishable from noise. The two other bands that we have here are C-band and X-band, and similarly, in contrast, the shorter wavelengths are more sensitive to displacement, but they tend to scatter off of vegetation, such as leaves or branches of trees and bushes, and so they can be a lot noisier in those vegetated areas. In this presentation, I am going to focus on freely available data that can be downloaded without having to have a quota or a project with a certain space agency. So the first of these data sets is Sentinel-1, which was launched by the European Space Agency. It has a spatial resolution of 5 by 20 meters, and it revisits a particular point on the Earth every 12 days. And in some regions, this is even increased to every 6 days. I'll also be sharing some results from the Japanese Space Agency's satellite ALOS-2, which has a particular viewing mode that has a spatial resolution of 60 meters and doesn't have the systematic acquisition of the entire globe, but you can still have images once or twice per year. And these are also freely accessible, and they have longer wavelengths, and so they're able to have a higher signal to noise ratio in these vegetated areas. So all of these satellites on the previous slide can produce SAR images, but what do these images actually look like? You've probably all looked at optical images at one point or another, but radar images, in particular SAR, are a bit more difficult to interpret. What we can see here is the amplitude and the phase of a particular SAR image over the Salt Lake City International Airport. What we can see in the amplitude image is the brighter pixels are related to areas that have a higher amount of backscattered energy back to the radar, and the areas that are darker have a lower amount of energy. There is also some geometric distortion based on the direction that the satellite is looking, which is oblique to the Earth's surface. The phase for a particular image is going to look like it is random, but it is related to, again, the distance that wave has traveled from the satellite to the Earth, and then back to the satellite. So if we take 2 of these phase images and we find the difference between them on 2 different dates, we can produce an interferogram, and that's what we see here. So we go from that seemingly random image to something that shows a coherent pattern that's related to the amount of ground displacement that has occurred. In this particular case, we're looking at a basaltic volcanic island in Vanuatu where there was a dike intrusion and uplift in the southeastern portion of the caldera outlined in black. In order to read this interferogram, we can choose a reference point that we assume hasn't moved. So let's say that's on the flank of the volcano, and we count the number of phase cycles that appear until we reach the maximum amount of displacement here just south of where the fissure opened. If we count these color cycles, which correspond to phase cycles, we can estimate the amount of displacement if we know the wavelength of that radar. So here we have more than 10 color cycles in this image, which corresponds to over 1 meter of displacement for this particular satellite. Another way to think about this is shown in this image here, where we see the radar's line of sight shown with this arrow and the difference that the ground has moved with this delta R. In this case, we have less than one phase cycle of difference, but in the case of this dike intrusion, we have more than 10 phase cycles. One of the important parts of SAR data that I want to, or InSAR that I want to emphasize, is that the measurement that we obtain is a 1D measurement in the satellite's line of sight, or LOS, and this therefore combines both vertical and horizontal displacement. So we have to know the direction the satellite is looking, which throughout the presentation I represent as these arrows, where the near vertical arrow is the direction the satellite is orbiting, and the arrow perpendicular to this is that line of sight. So in this case, the movement towards the satellite is a combination of uplift, but also possibly some eastward motion. There is a simplification that we can make where if we assume that there's no horizontal displacement, like if we have land subsidence in some areas, we can assume that if we divide our line of sight displacement by a certain factor related to the direction the satellite is looking, we can obtain a pseudo vertical displacement, but there may be some bias if we make this assumption and there is horizontal displacement. So in addition to knowing the direction the satellite is looking, knowing the orbit direction is important. So the satellite can either be orbiting towards the North Pole in its ascending direction or descending, moving towards the South Pole in a descending orbit. Another way to represent an ascending orbit, for example, is shown with this rose diagram, where the gray line is that orbit direction and the brown line is the look direction. So again, here's an example of those arrows that will be indicating which direction we have the ground displacement. So once we understand that the displacement we're measuring is in the line of sight, what is this phase difference actually representing? Because we're interested in the travel time between the satellite and the Earth and back, this is going to be affected by anything that influences that radar signal as it travels through the medium of the ionosphere and the troposphere. Here is a simplified equation that shows the different contributing factors that can affect that phase difference between 2 days. So any changes in the satellite's orbit, the topography of the Earth, ground deformation, and then any variations in the ionosphere or the atmosphere, and noise from the sensor itself. During the processing stage, we try and remove or correct as many of these contributions as we can. So we're left over with just the contribution due to ground deformation. And I'll show in some of the subsequent slides some of the signal that may appear, for example, due to that atmospheric phase delay. Once we obtain a map of the difference in phase at every point that we have a measurement, we then have to do something called unwrapping to go from wrapped phase to ground displacement. This is an automated algorithm that allows us to basically count the number of phase cycles between a reference point and any given point in that SAR or that InSAR image, and calculate the ground displacement between those 2 points. This allows us to obtain a ground displacement map that is between -infinity and infinity, as opposed to just a phase cycle between -pi and pi. Once we have these unwrapped interferograms, we can produce a network of interferograms and find the cumulative line of sight displacement between any 2 dates. The top figure here shows all the different interferometric pairs that we're using. And when we have many of these different pairs, it can help improve the measurement accuracy compared to a single interferogram by finding the signal that is consistent between pairs that are spanning similar time frames. The plot on the bottom is the time series that we obtain when we do an inversion of this network and find the cumulative displacement at any point on our displacement map. So this figure here shows an example of a landslide in southwestern, or slow-moving landslide in southwestern Utah, and we plot the displacement at a point where at this blue location, and this is motion. The red indicates motion towards this arrow here, so eastwards motion. And we can see that if we have an increase in that displacement of about 0.8 centimeters per year. And if we fit this displacement over time, we can obtain an average velocity for that pixel. And this is considering that we don't have any changes in that displacement. So I will be presenting some data that is the cumulative line of sight displacement, but then also some data that's that average velocity, assuming that our rate of displacement is constant. So I've kind of gone over all the background I'd like. Yeah, I'll leave that there for a second. I do want to make sure that everyone is familiar with the terminology that we're using. So to review some of the acronyms that I've used, SAR is synthetic aperture radar, which is a technique that produces fine resolution images that have an amplitude and a phase from a radar system. InSAR uses the phase from these two images to measure ground displacement and produce an interferogram. Line of sight is that satellite oblique viewing geometry. Ascending or descending corresponds to the orbit direction. And then we can either measure cumulative line of sight displacement, so that total ground motion towards or away from the satellite. And then from that, we can estimate an average velocity at a point on the Earth. And then finally, coherence is a measure of phase variability or phase noise, which I might mention. And this ranges between 0 and 1, with 1 having the lowest variability or the lowest phase noise, so the most reliable measurements. So my first job with this position was to produce a statewide line of sight velocity map for Utah using InSAR. And here we can see an example of some of the different satellite paths that we've processed using an online tool from the Alaska Satellite Facility, or ASF. This tool is really nice because it allows you to go online and you can choose 2 dates and you can produce an interferogram that's unwrapped and download it to then ingest into your post-processing or time series analysis. This is all free, and so it's accessible to anyone who wants to use it. And so it also greatly decreases the computational cost for an individual, since all of the interferograms are processed on ASF's remote servers. We then process these interferograms into a time series using a time series called software called MintPy, which is also openly accessible or freely accessible on GitHub and is open source. And then we can process in more detail some areas of interest using the Jet Propulsion Laboratory's ICE software, which is also open source. So we're really trying to focus on freely available data and software in a lot of this processing. So if we look at this map of Utah, we can see some large-scale variations in that color that span over hundreds of kilometers. And we assume that these are related to that atmospheric noise that I had mentioned that we can't fully correct. And so what we do want to focus on in this presentation is more local signals that are related to land subsidence or landslide motion. In addition to this statewide map that I've been working on, I also want to mention that JPL's Opera team is producing their own North America-wide InSAR product, which will be really interesting to compare with the results that we have and be able to update these results automatically in the future. Their current rollout has been mainly focused on the southwestern part of the US, where there is very high coherence with InSAR, but we do have a tiny corner of Utah that has been covered so far. So I just want to show the results for that here in this plot, where you can just go onto their displacement portal, choose a point, and then see how that changes over time. So now that we have an understanding of what InSAR is and how it can be applied, I want to focus on the first applied science question that UGS is interested in and thinking about land subsidence throughout the state. So if we have mass that's removed from anywhere in the crust, we're going to have an elastic response. But if we have this removal of mass from an aquifer due to groundwater extraction in excess of recharge, then we can have the opposite sign due to compaction of the fine-grained sediments in that aquifer. This animation is showing that compaction occurring as a result of a decrease in pore water pressure, which can cause subsidence at the surface above a confined aquifer. This porostic displacement can be recoverable or permanent, and in the case of permanent land subsidence, we can have a hazard as a result of this land subsidence, which is earth fissuring in areas of differential compaction. In this figure, we can see an example of those earth fissures forming beneath the surface. They can start out as hairline fractures at the surface, but as you have water infiltration, this can erode and lead into these larger earth fissures, which can be issues for infrastructure or people recreating in that area. These hazards are particularly of interest in the arid regions of the world, such as the Western US and Mexico. Here are some examples of ground earth fissures that have been observed in Arizona, where this is a particularly serious issue. That top imagery is some drone footage that's on YouTube of one of these earth fissures that's opened. And the bottom figure also shows the extent of earth fissuring in an area where we do have buildings and roads that can be directly affected by these fissures. I do want to mention that in Utah, we have observed that land subsidence occurs at rates of centimeters per year in basins that pump more than 43 million cubic meters per year. But the amount of subsidence does depend on the underlying geology, the amount of recharge to the aquifer, and other considerations. So looking at, in particular, at southwestern Utah, we will zoom into this average velocity map and focus on the area shown with this black polygon, where we can see those hot spots of displacement that are occurring in the areas where we have fine-grained sediments. Here are some results from the UGS Groundwater Data Hub looking at groundwater elevation trends over time from 1993 to 2023 for a few different areas in southwestern Utah. And we can see that the rates of groundwater decline range from about 40 centimeters per year to up to 1 meter per year. We'll first focus on the Escalante Desert and Cedar Valley, where we have some past groundwater budget studies that have measured the amount of groundwater decline from 1975 to 2005. And that's what's shown in this map here, with the greatest amount of decline shown near Barrel Junction in this orange area, where that decline has been up to 70 feet over that time period. There was also land subsidence that was measured in the late 90s according to InSAR measurements, and there was a development of a water management plan starting in 2007, and which was adopted in 2012 to address the concerns of the decreasing groundwater levels. Here we can see that interferogram from the 1990s, which spans 18 months. This was processed by some professor at the University of Utah for the Utah Geological Survey. And here we can see we've converted that line of sight displacement into vertical displacement, and we can see up to 7 centimeters of subsidence occurring within this region over that 18 months. The figure on the right is an earth fissure that was opened and eroded due to groundwater or due to water infiltration in 2005 in the region indicated by that red polygon. Here we have results from an updated time series looking at the period 2016 to 2024 using InSAR. And we can see that same subsiding area shown here with the displacement of up to 10 centimeters over a similar time span of 18 months. So we take that average velocity over the 8-year time span, and then we scale it down to how much displacement we'd expect to see over a year and a half. And that's what we're looking at in this map. In addition to that consistency of the spatial extent of the signal, except with possibly a slight increase in the amount of displacement, We can also see that there is displacement in Parowan Valley near Enoch and also outside of Cedar City. Here's an example of some ground fissures that have opened up in Enoch that were first observed while there was a subdivision that was being developed. This subdivision actually had to they had to stop construction on this subdivision after they had built one model home because they noticed the growth or the development of these fissures in the area. And here we can see some photos that were taken by a colleague in the hazards program from 2009 to 2010, where we see the development of that earth fissure in the newly laid cement. Here's also some drone footage of another fissure that was identified in a field outside of Enoch, taken by Bill Keach. So if we look back at that, the large displacement signal or spatially large displacement signal that we see near Beryl and Beryl Junction, we can plot both the average velocity shown in this map on the left-hand side, and if we look at GPS measurements within the area, we can understand if our InSAR measurements are consistent with what's being measured with ground-based observations. So there is a continuously operating GNSS station near Beryl Junction, which measures about 40 millimeters per year of subsidence over the past 12 years or so. Over a similar time period from 2014 to 2021, we can see also a displacement of a similar magnitude in this area based on our vertical velocity map from InSAR. In addition to looking at the vertical velocity in these regions, we also want to see if we can help our hazard mappers distinguish where earth fissures may form. And in order to do this, we've produced a spatial gradient of the velocity map to see where the rates of displacement may be changing the most over the area of interest. So what we can see here, although there is some noise from regions where we have no data, we can see that around the edges of that subsiding signal, we have quite high gradients in displacement. And if we overlay this with the fissures that have been identified in the field, we can see that many of these fissures do align with those areas of high displacement. So these products will hopefully help be able to assist mappers as they go into the field and try and identify regions of potential earth fissuring. So the next case study for land subsidence in Utah is Milford Valley, where there is currently an ongoing study to characterize the aquifer and assess water recharge and discharge. Here is an initial potentiometric surface map of groundwater elevation from 2024 that was produced by Greg Gavin and Catherine Lattig in the groundwater program. This, we overlay, or there's also evidence for well pad offset in this part of Milford Valley, which we can see in this photo with the notebook for scale. If we overlay cumulative subsidence in the area, we can see that InSAR also measures subsidence in the area around the agricultural regions. And if we plot a point that coincides with a USGS monitoring well, we can compare that InSAR measurement with the head change measured at the wells over time. So what we see here on the top plot is a time series of a Sentinel-1 measurement from 2015 to 2021 and the co-located head change measured from that USGS monitoring well. On the bottom panel, we can see total pumping and the cumulative departure precipitation from the average. One thing that we note is that despite continued subsidence of permanent subsidence of this area, there is no direct correlation between that long-term subsiding trend and the precipitation or pumping in this particular area. If we model that Sentinel-1 time series signal for this point, we can fit it with both that linear trend throughout time, but also a seasonal signal. And in this plot, the red line shows us extending that seasonal and long-term trend into the future, but also back in time. And the red dots here correspond to an independent measurement from a different satellite, SAR satellite, acquiring data in the early 2000s. Here we can see that long-term trend still fits that data from the early 2000s quite well, and it also fits that seasonal signal to the extent that we have data available. So if we look at the timing of where we have the highest groundwater elevation throughout a particular year and where we have the highest seasonal response in that InSAR measurement, we can plot both the head change and the vertical displacement change over time after removing the linear trend. And we can start to understand something about the elastic properties of the aquifer. So what we see here is plotting that vertical displacement from Sentinel-1, that change over the year, with the head change that also occurs on a yearly time frame. And if we fit the best line, we can obtain an elastic storage coefficient that tells us something or provides information about the head change that will occur given a certain amount of volume of water exiting or entering that aquifer. We hope to also be able to constrain other aspects of the aquifer system, such as the inelastic storage coefficient. And then also, if we know something about the depth of the aquifer, being able to estimate the skeletal storage coefficients as well using these data sets. Finally, for Milford Valley, I also want to mention that we can constrain the total amount of cumulative subsidence or compaction of those fine-grained sediments that's occurring over the region. And here we have two independent data sets of the same area spanning slightly different timeframes. And if we plot the cumulative displacement over the subsiding region, we find that over the past decade, there's been up to 10 million cubic meters of subsidence, volume of subsidence occurring. We hope to improve these measurements by considering bias that occurs due to vegetation growth in the fields. So that is a summary of the work that we've been doing to monitor land subsidence and better characterize the aquifers in Utah using InSAR. And then for the second part of this talk, I'd like to talk about slow-moving landslides and how we're able to monitor these and identify them using InSAR as well. So InSAR, so in Utah, we are particularly susceptible to landslides due to the presence of mountainous topography, steep slopes, and the local geology. There are millions of dollars in damages that that Utahns have to deal with every year due to landslides. And one of the most expensive landslides in US history was the Thistle landslide, which we can see here the extent of this event, which occurred in 1983 and cost about $200 million. The extent in yellow is the sliding event or the extent of the sliding that occurred in 1983. And there was a reactivation of an enlargement of this sliding that occurred later in 1998. And so this is an example of landslides occurring on pre-existing landslide features. So at the UGS, they conduct landslide recon and hazard studies, as well as inventories to identify landslide type and movement activity. They use geologic maps, aerial photographs, DEMs, and field visits in order to characterize whether a landslide is active or dormant or very slowly moving, which is what we can see in this map here from the Wasatch Plateau. They also monitor landslides that have been deemed as active using GNSS surveys and groundwater measurements. In order to supplement these observations, we'd like to better understand how InSAR can be used to measure displacement on slow-moving landslides. Here we show a sensitivity index that can be used to determine what slope angles can be best suitable for InSAR measurements. Because the satellite is looking at an oblique angle, there are issues that may arise due to geometrical distortion. And so this figure here shows that there may be regions in mountainous areas where you have shadows, that radar signal is actually not reaching the ground and backscattering off those areas. or regions where you have layover, where the signal might be distorted and higher parts of the mountain are actually returning the signal before lower parts in the valley. So taking into account the satellite viewing geometry and the slope angle and aspect of the terrain, we can produce these susceptibility or feasibility maps. And then we can actually compare this with the InSAR data that we process ourselves. So here we can see the results of an average velocity map from a Japanese satellite called ALOS-2 that I mentioned previously. This has that longer wavelength, and so it's able to penetrate through the vegetation in this area. And what I want to point out here is that this is the same area that was mapped by UGS about 10 years ago. And we can see some co-location of the larger InSAR displacement signals with the active regions that were mapped, as well as over here, but that there's also some noise that may be due to either that geometrical distortion or due to atmospheric noise. In addition to the limitations I mentioned previously, the amount of displacement and the size of a landslide can also indicate whether or not we're going to be able to identify the motion with InSAR. For example, if a landslide is moving too fast, you can actually alias that displacement signal. So if you have more than one phase cycle of motion between 2 pixels, then that's going to appear as noise and you won't be able to see that in your measurement. And so you'd have to use other approaches in order to measure the amount of displacement. So one final area where I'd like to focus on some landslide signals is in southwestern Utah, south and west of Zion. Here we can see Springdale and a large signal that is near Eagle Crags. The motion in this average velocity map is going to be indicating eastward motion for the red signals and then westward motion for those bluer signals. This map is derived from a time series where we have acquisitions every 12 days. And this is in a region with very little vegetation, so we have high coherence throughout the year and are able to use that C-band SAR sensor in order to obtain displacement measurements. In particular, this signal here by Eagle Crags is potentially high risk due to its proximity to a reservoir just at the edge of that, or at the bottom of the slope. If we look at a cross-section of the topography of Eagle Crags and the displacement, we can see the orange curve being the elevation of the region and the blue curve being that line of sight velocity. So we can see that on the eastern side of Eagle Crags that we have a displacement of up to 2 centimeters per year. Again, this red signal indicates 2 centimeters of motion towards the satellite, so most likely in an eastward direction, although it could also be a combination of vertical and horizontal motion. If we look at the time series for a few different spots where we have these slow-moving landslides, we can try and figure out any variations in the displacement rate over time. Here we can see that red dot, the red time series corresponds to the line of sight motion on the eastern side of Eagle Crags. The blue dots correspond to motion on the western side, and then the light blue corresponds to displacement near Cougar Mountain. We can see here that the rates seem fairly constant, but we'd like to better characterize whether or not there are any seasonal variations in these areas by applying corrections and decreasing the noise in these time series. Finally, I want to emphasize that these velocity maps can be used to also assist hazard mappers in the field to go and see if there are any other indications of active landslide motion. So Tyler, who is also in the hazards program down in Cedar City, went out in April of 2025 to Cougar Mountain and did find evidence for fresh sliding at the landslide scarp itself. And we hope to continue to utilize these InSAR measurements in conjunction with field visits. So the conclusions that I have are, and related to these 2 applied science questions, are that we identify 900 square kilometers of land subsidence in Utah at rates of greater than 1 centimeter per year, which we hypothesize to be related to excessive groundwater pumping. And we also identify more than 50 slow-moving landslides throughout the state with movement over the past year. And we hope that by continuing to monitor and study these areas that we can better answer the 2 questions that we posed earlier in the presentation. So moving forward, we want to continue to validate these measurements with InSAR with ground-based measurements from GNSS, also better improve our corrections of these measurements and improve our aquifer characterization throughout the state by continuing to monitor basin subsidence, and then also see how we can best integrate InSAR into our landslide monitoring. And then we have some future work that we'd like to focus on, and particularly really looking forward to the launching of NASA's and the Indian Space Agency's satellite NISAR, which should happen in the coming months. And there was a survey notes that came out earlier last month, I guess. And so there's more on the background of InSAR, but for a general audience. So if you're interested in that, I probably should have brought some copies, but we can grab some. And there's also a QR code to see the digital version. And I'm happy to answer any questions. So thank you.